Hey, my name's Casey, and if you want to see me walk through my LeetCode problems, you can subscribe. So LeetCode 139 word break. We have the word LeetCode, and they just want to know if we can build up that string from the list of words they give us. And in the list, in the words, we have Leet and code, so clearly we can make LeetCodes, and that's why we return true here. In this next string, all they're showing is that we can reuse words in the list of words that they give us to build up this string. So here we have apple, then pen, and then apple again, and then we return true here because we're allowed to reuse apple twice, and that's fine. And then in this next string, in this next example, we have CAT, so cat is in here. So we're going to try looking for sand, and sand is in here. And notice that we have nothing that could build up the OG. So we return, well, okay, so now we have to try cats, because cats is also in here. And let's see, do we have and? We do have and. But then again, we have nothing that could build up that OG, or that could, basically OG isn't in there, so we return false. There's no way that we can build up cats and dog from this list of words. Okay, so when I see this, my first thought is like, well, if you noticed earlier, I tried a greedy approach where I just took cat, and it didn't work. And I just want to go through my own example just to make that super clear. So my first thought is, well, let's just try greedy and let's just see what happens, right? Is there a way where greedy, say, returns false, but the real answer to the question is true? So let's just look at this example: cat, dog, owl, fox, and we have cat, dog, we have fox, and we have owl in my list of words. So if I was doing this in a greedy way, I would check a C in here, CA in here, CAT in here. Yeah, we have cat. Right? Cat's the first word in here. Sweet. So now we're going to check, well, is D in here? Is DO? Is DOG? Then dog, owl. And notice that, so dog is not in my list of words, which is why I have to keep going. So dog O, then dog OW, L, F, O, X. This would imply, well, and because none of this was in my list of words, this would imply false. But if we break this up, notice that we can make cat, dog, owl, and fox. So the real answer to this question is actually true. So greedy returned false when the real answer is actually true. So what I'm thinking now is that, like, well, we probably just have to brute force this. And once you've ruled out any other techniques that you happen to know, and we're just left with brute force, that leaves you the question of, are there overlapping subproblems? And let's just take a look at the example I have here. If you notice, when I found cat the first time, so let me separate that out. I'm only able to start searching from here for the next word because I found cat, which means I'm dependent on the thing that came before me, or AKA a previous subproblem, right? So, and the same thing, so I was only able to check D because I knew I found cat. Then I was only able to check DO because I know I found cat before. And it's not like I had to go back and find cat. In order to check DO, I don't want to keep checking cat over and over again, right? So this means, and same thing for DOG, I know I have cat, and I would have to find cat again in order to find DOG. So that means we do have overlapping subproblems. And no matter how I break this up, let's say I have, let's just do that one more time in a different way. So let's say I have cat, dog, owl. Let's just say, I found cat, dog, and I found owl afterward because I found cat, dog, I knew I could start searching from here, and that's how I found owl. And now I'm only able to start searching from here because I know everything that came before me was able to be found in my list of words. Or another way of saying that is everything that came before me was able to be built up from the list of words that I was given. Okay, so this definitely, so at this point, it's a brute force, there's overlapping subproblems, that should be screaming dynamic programming. Okay, so once you've committed to a dynamic programming approach, you should be thinking, you should be starting to relate this to your code solution a little bit. So you start thinking, okay, well, how am I going to iterate through this and solve this in a DP way? And I'm going to do the bottom-up approach. There's actually a couple different ways to do the bottom-up approach, but I'm going to do the optimal way. But I'm going to talk about both approaches. So anyway, let's just talk about one. The one way to think about this is, what if we just look for our potential first word? and we actually just want to find all of our potential first words, like in one iteration. And then in the next iteration, we want to find our potential second words based on what our potential first words were. And then we find our potential third words in the third iteration based on what our potential second words were, right? And so on until we hit the end of the string. And once we hit the end of the string, if that can be broken up, then we return true. So anyway, let's say I loop through. Let's just go with this example here. One way to think about this is, what if I just start at the beginning and I go, okay, well, a C in my list of words, a CA is CT. Okay, I found CAT and I mark this. And on this first iteration, again, I just want to find my potential first words. So we're going to keep going. Is CATT, is cat D in here, is cat do in here, is cat dog in here, cat dog is. So this is a potential first word. Okay, and then we keep going. We say is cat dog o, and then we just do the rest of the string. And our only two potential words starting from the beginning of the string are cat and cat dog. Okay, so now we want to loop on the second iteration. We want to start searching based on our previous words that we found, or for our potential first words. So for example, you can almost imagine like an IJ thing going on here. So in the first iteration, I did something like this, where I just kind of started back here and J was just moving along throughout this. And then on the next iteration, we're going to move I to our potential first word. And we're going to say, okay, now is D in here. And then you move the J, is DO in here. You move the J again, is DOG. And then you would just keep moving the J down the line, looking for any potential second words that you can use. And then you'd have to increment your I to the next potential first word. And then you do the same thing. Start looking for a potential second word again. And here you would say, okay, well, is owl O in here? Is OW? Is OL as your J is incrementing down? And you'd mark this as true. And I guess we could just finish this example. So, and then you would say, is owl F in here? So our only potential second word that we found so far is owl. And then we're going to check. My cursor is doing weird things. Okay, then we're going to check owl F, then owl FO as J increments down the line, and our only potential second word is owl. And then you increment I to this potential second word, and you check, okay, now is F in here? Now is FO in here as J increments, and then your J will increment again, and then finally we're going to say, is FOX in here? And it is. So you would mark this as true, and as long as once we get to this last letter, if this ends up being true, this means that we have everything that came before me could be broken up into words, right? So once we find this last character, or once we get to this last character, we know this is my last word, and if it ends up being true, then that means the entire string can be broken up into words. Okay, that's one way to think about it, and that we're not going to. Notice what I was doing was like, I guess I should mention it since I already talked about it. So in order to check if, let's say when J was here, in order to check if F was in my list of words, I would actually have to, in order to do this efficiently, I would have to turn this into a set, because notice they gave us a list, and I would just check if is F in my set, is FO in my set, and that would be O of 1, a bunch of O of 1 checks to see if F and FO is in my set and FOX is in my set. Okay, and so that's one approach. Another way to think about this problem is, okay, let's just say we don't change this into a set. Let's just take what they gave us, the list of words. Well, what if I just loop through my list of words and I say, okay, is cat a substring, or is this a prefix of my string? And this, again, it's the same concept though. We're just looking for those first potential words, and in another iteration we're going to look for our second potential words. So right now we're looking for our first potential words. So we're going to check, hey, is cat a prefix or a substring of cat, dog, owl, fox? And you could just do an s dot starts with words at I or something, to check if it's a prefix. And if you really want to get optimal at this, which I don't think I'm going to I might if I anyway, you could optimize that with a try because it's just prefixes, but we'll talk about that later. So cat. So back to this. So we're gonna check, is cat a substring or a prefix of cat, dog, owl, fox? It is. We're gonna mark this as true. And then we're gonna check the next word. Is cat, dog a prefix? It is. And notice we're starting from the beginning of the string. So let's mark this as true because this is also a potential first word. And now we're going to check if fox is a substring, starting from the beginning, and it's not. And we're going to check owl, and owl is not a prefix of this entire thing. Okay, it's a suffix, but it's not a prefix. So we're looking for that potential first word. I'm going to keep saying that. So now that we found our potential first words, which are cat and cat, dog, we want to find our potential second word. So we're in a second iteration. We're going to check, it's the same concept where we start from here now, where we go, okay, now, are any of these words a prefix of dog, owl, fox? And, cat is not a prefix of dog, owl, fox. Neither is cat, dog. Neither is fox, and neither is owl. So we can just continue on to our other potential first word, which is cat, dog. Let me put this back. And now we're asking, okay, now are any of these words a prefix or substring, well, sorry, when I keep saying substring, I should just strictly say prefix. So a prefix, substring, whatever you want to say, but strictly a prefix. So is cat a prefix of owl, fox? And it's not. What about cat, dog? What about fox? What about owl? Owl is a prefix of owl, fox. So this is our potential second word. So we're going to mark that. And then, once we loop through all this, we'll then move on to another iteration where we look for our third potential word. And, we'll check so now we're here and we're checking. We want to know if is cat a prefix of fox? It's not. What about cat, dog? What about fox? Fox is a prefix of fox. Or it actually is equal to fox. It's also a prefix. And now that we are at the end of the string, and this is marked as true, then we know the entire word, this entire string, can be built up. I'm trying to highlight the whole thing. You guys know what I'm saying. This entire string can be built up from the list of words. Cool. So now let's actually code this. And this is the approach we're going to code out. It's the most optimal DP approach. So yeah, let's just code it. So when you do DP, so notice that this is basically just an array of where we're marking like indexes with just like true. Like it's true if we found this word up to this point, and false if it'll just be false otherwise, right? So this DP array, this is just a really common thing. Oh, I don't know why I made this in it. It should be a boolean. New boolean s.length +1. Okay, and I'll explain this +1 in a second. But it definitely has to be the length of the string, right? Because we need to mark all these little spots as true or false. And it'll, by default, this boolean array has all falses in it. And the reason for the +1, this is just a really common thing with dynamic programming to make you just make this first value because, okay, it just, when you think about dynamic programming in general, like we answer the question to a subproblem based on the previous subproblem, but the very first subproblem has no previous subproblem. So we're just like creating that. For the very first subproblems, we're just initializing this to whatever allows those first subproblems to compute, if that makes sense. So here, I'll actually leave this blank for now. I know what it's supposed to be, but I just want to keep going and we'll walk you through the logic and then you'll see what this has to be to make everything work. So yeah, let's just keep going and then you'll see. So we need to loop through our string, or we want to create substring. So remember in the beginning, we want to find our potential first word and then we want to find our potential second word. So in the beginning, we want to use the entire string. So let's see. You'll see what I'm doing in a second. So string substring equals s dot substring of starting at I. Okay, so in the beginning, I is going to equal 0. So that means that we're just going to take the whole string in the beginning. So this s dot substring at 0 is just the original s. Okay, well it returns a brand new string, but it's the, yeah, I think you guys all know how substring works. Okay, so this is just the entire string in the beginning. So this would be cat, dog, owl, fox in our case, and we want to check if any of the words in our list is a potential first word. So let's just go with, and we do that by checking if it's a prefix. So if if substring dot starts with word, then dp at, so we need to mark, so let's say we found cat, right? If we, let's just bring this down here. Yeah, let's highlight, let's just bring this all here. So let's just say, okay, so this first word is going to be cat, right? And we're just checking, is cat, dog a prefix? And now we want to mark this index as true. And remember that I did I added a +1 up here. So this is going to be, let's see, I plus the word dot length. And so this would actually be, let me see, this would be index 4 in our, so no, actually, wait, no, this is index 2 here, which means it's index 3 in our DP array. And word.length is 3, so this is fine because cat is 3 letters, 0 plus the word length. Okay, we're going to mark this as true. Yeah. And then we'll do, so then eventually we'll do cat, dog, and cat, this will be true. And then I, which is 0, plus the length of cat, dog, will be marked as true. Okay, so is that right? I might be off. I feel like I might be off by 1, but we'll see. Yeah, I think conceptually you guys see what I'm trying to do, but if I'm off by 1, I'll figure it out later. Okay, so let's keep moving on. Oh, and then at the very end, we're going to return whatever's at the end of the DP array. And so just be s.length. I could do dp.length -1 or whatever, but this is the same thing. And now for the second iteration, and this is where I'm going to make it clear why I have this dp0 here. So on this next iteration, we found our potential first words, right? Because we marked them as true so we marked these two as true up here. Now we need our I to move to this in our DP array. So because we don't want to check, or we need to start searching after our previous first words. Yeah, we need to start searching after our potential first words or our previous words that we found in the previous iteration. So what we want to say is if not DPI, which means that the previous thing that came before me couldn't be broken up into words, we're just going to continue. And the reason we have, so now I can get to this +1 that I was talking about earlier. So notice that I is 0 here. If we just left this as, let's say I just made this false. Because these are all false, or this whole array is false, right? Well, if I just say if not false, then I'm going to continue for literally everything. So I need this initial case to just be true for that very first iteration. Because in the, I'm having a hard time explaining this, but I think if you've seen DP before, you know that there has to be some case for all the problems that don't have no previous subproblem, and you just initialize it to whatever makes that first iteration run. And so we just set this to true so that we can execute that first iteration, because then not true is false. And so we skip the continue, and then we just keep going down here executing this for that first iteration. And then on the next iteration, anything we didn't mark as true will just be skipped over. So we would skip over C, we'd skip over CA, and then I will hit this T in cat, and then we'll start searching from, then we'll start creating substrings from, say, we'll do D, then DO, then DOG, then dog O, owl, fox. Okay. I'm sorry if that's a little rough. It's a little hard to explain like the little intricacies, but I think if you like listen to me, maybe repeat this part of the video and like walk yourself through the code, you'll see what I'm trying to say. But anyway, let's just keep going. So we just skip to the word that we found in the previous iteration, found the substring, and I think this is actually done. So I'm gonna run this. Oh, I need to comp this out. If substring, what's wrong with this? Starts with, and cool. So this is actually done. And let me take out these, let me just clean this up for really quick. Actually, this is pretty clean. I'm debating on whether I want to show you guys the trie optimization. And actually, no, let's go through the time complexity of this. If I go to the trie, it's going to be a longer video. But I feel like now that I've mentioned it, I feel like there's going to be people that want to see it. So, all right, it'll just be a little bit of a longer video. But anyway, let's just do the time complexity of this, and so that you can understand why the trie, adding a trie to this would be a little more optimal. So, let's just get rid of all this. Let's do time complexity. Okay, so what are we doing here? We got O, we'll just call this O of S. This loop is, so I'm just saying that S is the length of the string. And let's see, we're doing S dot substring. So we're just going to say this is bounded, upper bounded by O of S, because, you know, S dot substring, okay? Because we have to create a new array and move it over, or copy it over. And this would be O of, I'm going to call this O of, we'll call this O of K. And I know I have a reason for not calling this O of W, but the O of K, where K is the number of words, okay? Or words, actually, what you could just say words dot length, or words dot size, okay? And okay, so substring dot starts with, what is this? So this would be, so if we assume that most of the words in our list of words are shorter than the string that we're trying to build up to, then this was just big O of W. So W, I'm going to say, is the word size, or average word size. We can say this is an amortized O of W, so the average word size. Okay. I might have to think about this for a second if this is absolutely correct, but I feel like you guys, this is good enough. Okay, so let's keep going. So now this would be O of KW. Let's just put this off to the side. So this would be O of KW, and then this whole thing, because we have an O of S in here, this whole thing would be O of S squared plus S times K times W. You know, if you want to put the little things in there, you can. I could just leave it like that, SKW. Okay, so now, so that's the time complexity. Space complexity, I'm sure you guys can figure that out. And also keep in mind that this is also O of S space, by the way, for substrings. Just to don't like just overlook that. But anyway, let's talk about the time complexity a little bit more. So like, how can this be optimized with a trie? So notice here, I'm looping through all the words, and I'm just checking if all these words are prefixes of my substring here. Because if this substring starts with this word, I'm just checking if all these words are prefixes, right? Which is how we end up with O of KW, where K is the number of words. Oh my gosh. K is the number of words, and W is the average word length. Okay, so the way we can optimize this with a trie is, I don't want to code it out because it's going to take another 5-7 minutes or something, and I'd have to walk through it. So you can actually eliminate this K variable, which is K is again is the number of words. No, wait. Yeah. K is the number of words, and then W would be the average word size. And the reason is because in a trie, we would just build the trie. We'd pass in, we'd loop through all of our words that were given, pass them into the build the trie, pass them in, and we would just when we pass in our substring to say, hey, is our substring in this list of words? As you're looking for the substring, as you're looping down the nodes or going down the nodes, however you want to say it, you're going to check, hey, is this a word? Is this a word? Is this a word? And anything that is a word is a prefix of my substring. And that would be, so normally when you loop through a prefix, when you're checking if your string is in the trie, that is normally upper bounded by the length of the string that you're checking, right? Because you're assuming that all the words in your trie are longer, or most of the words are longer than your the string that you're checking. So like, for example, normally you might check in a dictionary is cat in the dictionary, and most of the words are longer than cat. But in this case, this is a little special problem because the string that we're building up to, it's safe to assume that it'll be longer than most of the words that were given. And our trie is built up from these shorter words. So when you're actually going down the trie, it's limited by the length of the words in the trie and not by the length of the string that we're checking is in it. And I know that hopefully you followed that. Maybe replay this part of the video. If you have any questions in the comments, you can comment down below and I will answer them. But yeah, so that's so basically what it would end up happening is you implement this with the trie at the very end. If we had KW, you would actually get rid of this K because checking for all the prefixes would just take O of W time because you just check node by node by node, and eventually you're going to hit the end of the trie or a leaf node in the trie, so that'd be limited by O of W. And then the time complexity for a trie, which, let me write that down for a second. A trie would be the exact same thing, but you would just you're removing this loop essentially. And we could get rid of the K here. So that would be a little bit more optimal. And that would be the absolute most optimal solution, at least that I know of. But anyway, sorry if this video was a little rough. It's a little hard to explain DP problems because, it's an array and yeah. DP problems are a little tough to explain. But I did my best. Hopefully, if you guys have any questions, comment below. And if you enjoy the video, give it a thumbs up and you can subscribe if you want. So later. Bye.